Okay. So as Felix explained, you can define A1 localization very easily and prove a few things about it. But so then the natural thing to try to do is to actually compute the motivic homotopy groups. And so I've tried doing this in this case. So I was not successful so far, but you know, I have some partial results that I want to present here and explain a bit the ideas. So the first remark is that I followed Morel's book on motivic homotopy, or at least I was heavily inspired by it. And
is it clear what it means? Compute physics? What do you mean by you mean 1, 0 or 0, 1?
Definition. Let's be applied. So phi1 A1 x is equal to the omega type of the shape 1 of x. So shape 1 is the modality that builds one truncated A1 local types out of any type that Felix introduced. And so we know this is a 1 type, so the omega is indeed a set. We also know that this is A1 local, so P1 A1 of x is A1 local as a group. And so remark is, let's say I don't expect that P1 A1 of x is equal to P1 of the A1 localization of x. So okay, maybe I don't expect this to be provable, although I don't expect it to be refutable either. So yes, so then there's the question which definition to use, because both look reasonable. And so trying to compute, I was able to say more things using this one, so maybe it's the best one, but maybe not. So okay, so now let's use this one. And so the goal is to compute, or at least to try to compute this P1 for projective space. And so yeah, the core, intuition, let's say, it's that we have a fiber sequence PN, and this should be universal A1 cover in some sense that I will make precise soon. And so then we should be able to compute P1 of this using the usual universal cover business. And so actually, to define universal cover, we can do this actually for any modality. You have a theory of modal universal cover that works well. So let me give a definition. The fiber sequence, say G, X, Y, is a universal A1 cover of Y. If we have the following conditions, so say G is a set, which correspond to the, like actually we could ask for all the fibers here to be set. It would probably be more natural to do. So let's call this map F. Fibers of F are sets. So that's how we would define cover in plane homotopy type theory. We need an extra condition. So we want F to be what is called shape one étal. So for any modality, you have a notion of étalement for this modality. This adds to the confusion again, because this is not the same étal as in the formally étal modality and neither the étal shield modality. But I will still use this terminology because that's the one you find in the literature. And so what does it mean for F to be A1 étal? It means that the square you have like this. So here you use the shape one localization. Here you have F. Here you have shape one of F. And you ask that this is a pullback. So that's the definition of being shape one étal. And so remark. Yeah, let me write it somewhere else. And only if the fibers of F are shape one modal, local, let's say. But this is not enough. You have an extra condition, which is that the map from Y to the universe of shape one local type, the fiber map, to factor to the shape one localization of Y. So you always know that there is at most one lifting here by general stuff on modality. So, but the condition of being shape one étal means that there exists one. And so now I have a third condition to add here. So here I've defined A1 cover actually, but I'm interested in the universal one. So in plane homotopy type theory, we would ask that X is simply connected to get the usual definition of cover, but here we use shape one, so we ask shape one that's contractible. And so, okay, and so the idea is to use this to compute I1, and so first, lemma. Let this be a universal A1 cover. Then G1 A1 of Y is equal to G. Okay, so let's prove this, and the proof is very easy. So we have a fiber sequence, so we know we have a pullback like this. We know this is shape one étal, so we have a pullback like this. But actually, this is equal to one. And so by pasting the pullback, we get that G is the loop space omega 1 of the shape one of Y, which was the definition we took of this.
So it's about the intuition. So the second map is a projection. What is the first map?
So it's you see this as the sum of V on VA times of Vn plus 1 minus 0. You have an inclusion of An plus 1 minus 0. And the fiber of this is actually the here you could extend here. And the fiber of this map is the loop space of this one, which is A times, which I mean is not a
I want to see the group structure on G directly, or
so no,
you prove that it's equivalent as a type.
Yes.
Yeah, and then
yes, and so here there's indeed something missing that this doesn't prove that the group structure is the same. I really expect it, but it's not proven by this seventeen.
I mean, imagine it's not a group in the definition, but yeah, of course, if you say it's the unit in R, it happens to be 1, and so
yeah, but in the definition, G is not a group.
It's normally some kind of vector transformation associated with so you have some direction between those.
Yes. So, but it's not in this book. But yes.
Okay, so what you define when you have a shape 1, the entire left and it should have a Galois group, which should be, this should be G.
Yeah, you always have the monotony of the shape 1 as a group point acting on the fibers.
Yes. Yeah, so you always have a group action because the group, but I did not check that the group induced was the same as the one on 8 times, but I mean it's the case. It's which of course. But okay. So yes, so we have so now the idea is to try to have this as a universal A1 cover. So we encounter some problem. So the first problem is that actually this is not A1 local, as Felix explained. And whereas the G here has to be A1 local, because the map is shape 1 étal, so its fiber are shape 1 local, so in particular they are A1 local, and so but here Felix explained the solution. So recall if X is a smooth scheme, then the localization from X to the formally étal replacement is in A1 equivalence. And so what we do is that we consider the formally étal replacement of Pn, the formally étal replacement of An plus 1 minus 0, and the formally étal replacement of A times. So so this is a better candidate for the universal cover. Thank you. So,
I mean, we were not able we were only able to prove that the units are not I mean, you only were able to prove that we cannot prove that the units are A1 local, but
what?
we had the not in your. I mean, when you prove that we cannot assume that the units are A1 local, you use Neapolitan's.
Yeah, so A times is not A1 local, but this is A1 local. And it's actually the A1 local replacement of A times.
Yeah, but it's also a problem with this proof, but I just wondered whether maybe we should maybe make A1 being A1 local a bit weaker by also making the units local, multiplicative proof local as well. I mean, as you said, it's classically the case.
But I mean, it's due to the particular setup that is classically most commonly used.
You can still look at this nullification and nullifies it both to A1 and A2.
Yeah. So, and then
maybe that's better behaved.
Yeah.
So that would be.
So what do you mean? How should we do this?
So you mean localize not only at A1 but also at the units.
Okay. So
Here you don't say that what you want is for this to be local.
Yeah. So
at the
Yeah.
what?
if you localize it, the units as well, you make them contractible. The interior to use it as a separate.
So you force things to be contractible, but you cannot force them to be model. If you see what I mean.
But what about the classical circle then?
It's local, it's not contractible. Right?
Okay.
That's what I got.
The classical circle.
No, I mean the classical is. I mean the argument against localizing at the units was that we still would like to have the units as a circle.
Yeah.
And classical, there's no problem because it won't become contractible.
Yeah, so it's okay.
Okay.
Yeah, okay, so here we know that this formally étal replacement is A1 local. So let's consider this sequence. So now to show that it is universal, we have to show that the shape 1 replacement of an plus 1 minus 0 is equal to 1. For n greater than 2. So here, so I will not prove this, but you can, or maybe I will prove it actually. You can prove that this is A1 equivalent to the iterated join of A times, which we iterate in plus 1 times. And so yes, so the idea of the proof is to cover this by 2 pieces. So for maybe I do with 2 minus 0. So on one hand, we consider these pieces. To show like this. where you cover by the one where the left coordinate is invertible and the one where the right coordinate is invertible. And so when you A1 localize, this is this actually gives a brush out where you have you A1 localize here, so you get A times here. You get A times here.
You don't really localize, right? You just write something down which is equivalent.
Yes, yes. So what I mean indeed is that you have a threshold like this. You can define maps from here to here by using the identity here. Here you use simply the projection as well. And here you have an induced map by the threshold property. And you know that the three maps here are all A1 equivalents. So this one is the identity, this one just project A1 out, and this one as well. And so from this, using general stuff about modality, you know that the map between the thresholds is an A1 equivalence as well. So from this, you get A2 minus 0, A1 equivalent to the join of A times and A times. And you can actually iterate this construction to get this.
Was this 10 bigger than 1? Yeah.
So for this part here, yes. But then to conclude, you use that the shape one of sorry, just the one truncation of this is equal to 1 if n is greater than 2. So by using property of the joints. And yeah, and so from this, you know that the shape 1 is equal to 1 as well. So you know that the modal pack for this modality, it is 1 truncated. And by abstract things on modality, you know that connected goes the other way. So if you're 1 connected in the sense that you have a 1 truncation, which is 1, you know that this holds as well. So yes, so we're getting a bit nearer to having this universal cover, but still not quite. So we know that this is an A times, formally a replacement of A times torsor by looking at how it is defined. And so lemma, if PG is A1 local, then G torsors are shape 1 local. Okay, so the proof is not complicated. So okay, let's say you have a map from X to BG, which is a G torsor over X by definition. So first we need that its fibers are A1. So we need for all X in X, P of X shape 1 local. But PG A1 local implies the loop space of PG A1 local. Because A1 local type are closed by identity type, this is actually equal to G. And so then this implies a G-torsor A1 local, because they are merely equal to G. So okay, we know that the fiber of a G-torsor are all modal. And then what we need to do is just to factor the corresponding map through A1x to conclude that it is étal by this this equivalent characterization of shape 1 étal map are the map which fibers are shape 1 modal and such that the map, the fiber map factors to the shape 1. But this is A1 local by hypothesis. And this is the one type, so it is shape 1 local by definition. And so we have a link like this, and we can conclude. And so yes, with all these ingredients here, so we know that for n greater than 2, okay, let me just write this down properly. So let's say the proposition. If the delooping of the formally étal replacement of A times is A1 local, then greater than 2. And so the proof is just, we just have to get all the pieces that presented together. So you start from the hypothesis that this is A1 local, so you know that any G-torsor is shape 1 étal. And so you know that that this map here we know that this is shape 1 étal. Then we need to show that this is shape 1 connected, and we have it over here. So yeah, so here we have the property for an plus 1 minus 0, and we need it for the formally étal replacement. But we know that the formally étal replacement is equivalent to is A1 equivalent to the type, because we have a smooth scheme. So we know that shape 1 of the thing in the middle is equal to 1. And yeah, and so from this we conclude that G1, A1 of this is equal to A times, and this is A1 equivalent. Since Bn is a smooth scheme as well, we know that this is the same as this. And so yes, so that's not the computation, because I have this hypothesis on this delooping that I cannot prove. And so yeah, I don't know if it holds. I don't even know if it's reasonable to expect it to hold. But at least if it holds, there is this computation that goes through using universal cover. And I will conclude my talk here. Thank you.
Couple of questions. So recall that David S. Myers has some arguments for why in synthetic differential geometry, discrete groups have discrete loopings. Does that not work here? What's the obstacle?
So I think, from what I understand, the argument needs a crisp modality.
Oh, okay.
And the crisp modality, we don't have it here because we did not assume it, but we even cannot assume it because it would imply A1 local type to be a higher topos in the model of homotopy type theory, whereas they are not.
Yeah.
Yeah. David's proof uses like a lot of the flat modality.
Yeah.
I mean, in ACTA, you have to add some flex for the flat mode to make it go through. So,
yes.
Okay, another question is, what about motivic Algebraic Moeneclaey spaces? Do you have any idea how to construct these? You have the motivic NN spheres or NK spheres. The NN sphere is like the Pn co-fiber or Pn minus 1. And so you need this motivic truncation to make it into the motivic Algebraic Moeneclaey space. Okay.
could you maybe briefly explain what it is? I don't know.
Yes.
I
don't know how much we can expect. But we would like to go back to intersection theory. In A1-homotopy theory, represent the child groups. And these are represented by sometimes the notation is something like this, kind of truncation. If we had this.
So what is this operation?
Oh yeah, so it has a very site-specific definition where you take something like at a representable, you look at the closed, irreducible subschemes. I don't remember. I could look it up in resources. But yeah, so the question is there a more intrinsic way of getting your hands on these objects? Could you define this, and if it's Nabila group, just do good. I don't know enough to to do more than ask the question at the moment. Sorry, there's maybe something like that.
Yeah. By the way, I have a question. My shame, I don't know how to answer. Let's look at P1A1 of S1. What is this thing? So I would really expect it to be easy, but to prove this, I would need S1, A1 local. And this I don't know. You have, when you try to prove this, you have a Z dorsal over A1, you want to prove that it is trivial, and I don't know how to do this.
I mean, I've written down a sketch somewhere for the case where A1 is overt.
Okay.
But yeah, don't know what happens otherwise. Yeah. So in particular in characteristic 0, we know it's that.
Yeah, which is a good start, but you should hold all the time, and it shouldn't be difficult, I feel.
Yeah, I mean, maybe we can find something in the literature that in characteristic P, it's just not what you expect. I don't know.
Or maybe we don't know anything about characteristic.
Yeah, I don't know what the literature says on questions like this. I think in the usual setup, you always say characteristic 0. I'm not sure. Like if you use the Moeneclaey side.
So, thank you.